All right, cool. So let's talk a bit about the covalent networks, just so you guys are aware of um, how graphene works, because that's obviously going to be the one that you're researching for your chemistry journal. So when we talk about covalent networks, there are three different types. There is the 1D. So to start, so we can talk about covalent networks. Yeah. And these fall into one of three categories. You have the 1D, the 2D, and then the 3D. So they're going to have very different properties depending on what we are talking about, and it does parallel when we talk about like dimensions. So when you think about drawing, if you're drawing like a cat on a piece of paper, that's considered a 2D drawing because it doesn't have the three-dimensional shapes. But if you were going to draw something like a cube, like that, that is now expressing three-dimensional shape. When we're writing on a piece of paper, that is a two-dimensional plane. When we're thinking about models and things, then we're talking about three-dimensional plane. So that's what that's referring to when we talk about 1D, 2D, and 3D. It's just a reference point into the dimensions that are present in that matter, or in that network, I should say. So first off, the 1D covalent networks. I'm just going to circle it and then write the notes down here. These ones are long chains, often polymers, and polymers are repeated structures. So, for example, you basically have like a string of beads, the way I would best describe it. And this is a very oversimplistic model. It's just to kind of give you an idea of what we're thinking about. Now, with this 1D substance, it's going to have multiple chains that are like mixed together. So for example, you'll have a chain that's on that side, and it'll also be in the three-dimensional space as well. So this might be stacked below it. There might be another chain that's stacked in front of it, another chain stacked behind it, another chain on top of it. So it's like you have to think about it as a three-dimensional network that like there's all these chains here. With these chains, so I've only drawn two for simplicity's sake. The bond that's between our atoms are covalent bonds. And that is between our atoms. But when we think about properties of matter, we're thinking about it in the solid state and what are the bonds holding together in the solid state. When it comes to covalent networks that are 1D, what is holding it in this solid state are these weak intermolecular forces. I'm just going to change colors. So I represent them as dots. When you guys talked about covalent molecular solids, they were held together by these weak intermolecular forces as well. So those are weak intermolecular forces. Are we good so far? So that is what holds together the solid. All right. So when we are thinking about 1D covalent networks, what we're often thinking about is plastics. That's probably the most basic example of it. And plastics in comparison to 2D and 3D networks will often have low melting and boiling points because what's holding that solid together is just these weak intermolecular forces. Since it's the weak intermolecular forces that are holding these solids together, it doesn't take a lot of energy to break it apart. So that's why you see plastics melting fairly easily. Depending on the type of structure you make with this polymer, you can change the qualities of that plastic. You can make it heat resistant. So some plastics like silicone, you can actually use to bake like your muffins in, and that's because the structure of that plastic is a bit stronger, so it can withstand the heat of an oven. The different polymers can also affect what sort of properties that plastic has. So some plastic is really soft, like the one that's in this wire to allow the wire to bend. Other plastics are really hard, like in the document camera itself, so that way it holds shape. So these are all still 1D covalent networks, but they have slightly different structures in what is making up that 1D network to then change its property. So it could be a different kind of chemical that's there, and it's usually a repeating pattern. And these are like thousands and thousands and thousands of lengths long. When you melt stuff, and this is one of the problems we run into when we're trying to reuse plastic, is that when you melt it, it disrupts the structure of this, and so you get clumps of plastic. And if you probably would have noticed that whenever you accidentally melted plastic, it changes shape, and then it's not as useful as a material. So that's one of the problems we run into when we're trying to reuse plastic, is that it's difficult to do that because it's going to lose a lot of its qualities. The other thing is that when we melt plastics, there's going to be plastics of different qualities, and so mixing them together might make it impossible to get it to be a useful substance later. So that's why they want you to separate your soft plastics from your hard plastics, and they only accept plastics with like the number 5 on there and stuff like that. So that is what that is referring to. Are we okay with that? All right. Now let's talk about the 2D covalent network. This one is really just one that we talk about, or there's only one substance in that category that we talk about in level 2 chemistry, and that is graphite. So what has happened with graphite is we have a carbon molecule, and it's basically set up like these honeycomb rings. I'm going to have to draw, which I don't like doing because it's really hard for me to do that. Oh, I hate doing this. I should have just printed it out. Okay, so you see how that's like a honeycomb ring, and this is like a flat sheet of paper because we're talking about a 2D dimensional shape. All of these little corners here are carbon atoms, like that. And what happens is you have multiple like layers of sheets of graphite. I'm not doing this terribly well because I'm not much of an artist. So this would be like one layer of the sheet. This is like the second layer of the sheet. So these, again, the bonds between the carbons, these are covalent bonds again, which is why we still call them covalent networks. Between these layers are going to be the weak intermolecular forces, like that. So, and there's lots and lots of them. So it's very different to the 1D network because there is a more structured organization to it. So that is our intermolecular forces. So again, these are going to have certain properties that will make them different from the 1D and different from the 2D. At this point now, we start getting to higher melting and boiling points, so it does take quite a bit of energy to break everything and get graphite to go from a liquid, graphite to go from a solid to a liquid. The other thing to keep in mind that is really cool about graphite is that it can conduct electricity. So when we look at this carbon atom here, carbon wants ideally to have 8 valence electrons, so that's when it's most stable. So it's going to be sharing electrons with the neighboring carbons. However, it's only sharing electrons with 1, 2, 3, 2, 4, 6. So what that means is that we are going to have a leftover electron from carbon, and it's going to be a delocalized electron. And one of the requirements that you're going to need in order to be electrically conductive is a mobile charged particle, either an ion or an electron. So in this case, graphite is going to be conductive. So that gives it a lot of unique properties. Like that. It also will feel slippery because it can have these weak intermolecular forces, so these bonds can break and remake, and the 2 layers can slide over each other. And that's why we have graphite in our pencils, because it can have that smoothness to it, and actually you can leave then some of that graphite on the piece of paper. And this is conductive, so if you were trying to stick this into a circuit, it would work. Why do you think we don't use graphite? Like, why do we not make graphite wires? What happens when you break a pencil in half? You break a graphite, like you break the lead in half. Does it bounce its shape back, or does it shatter? It shatters. So that's not useful to us property-wise for wires, because we want wires to have that flexibility. So you can see how we choose what state of, or what substance we make things out of based off the properties that it can provide. Both of them are electrically conductive, but in this case, we need it to be flexible shape-wise. Now, your internal assessment is going to be looking at graphene, slight changing in the spelling, and that is something that is a recent chemistry development, and that's why it fits under this standard that you're looking at. You're looking at chemistry developments. And what they have done is they are trying to get single layers of the graphite off. And they've used tape to do that. It's a real crazy thing. And all they did was just like simple like house tape, like normal tape that you tape papers to. And they have tried to separate the layers in the graphite. Now that's really important because now we can actually start using this material because this is highly conductive, it's very light, it's really strong. So we can use this to build certain materials and technologies and equipment. So that's why that internal research is on that, because it's a developing technology. So that's the 2D. And I'll briefly talk about the 3D. I'm just mindful of time. We end at 25, don't we? I think, yeah. The 3D is the last one. So the 3D, there's two that they talk about in level 2, but there's definitely more. The one that I will talk about is diamond, because diamond is following this trend of carbon, which I think is useful. So when we have, oh, no, I can't draw it. Okay. So it's like this giant, I do a really bad job trying to show that the carbon's attached to like 4 other carbons. So it's like this giant network of carbons just attached to carbons. It's a really, I'm going to look up a picture to show you because I'm not good at drawing. It's a really structured, organized manner, and it's really, really strong. So in this case, we only have covalent bonds. There are no intermolecular forces in this case. In this case, too, when we look at the carbon has 4 things bonded to it. So it has maximized its bonds. It's now gained another bond, which is going to help with its structure. Diamond is very, very strong. And so that changes its property. The downside is now that we've gone from a 2D structure to a 3D structure is because we've added an extra carbon into that bond, we no longer have that delocalized electron. So now we've lost the property of conductivity. So that's kind of what you're thinking about when you're thinking about all these different states. So those are the 3 different covalent networks. The one you guys are going to be focusing on is this one. But I figure it's useful to know the other 2 so you have a reference point. Cool? Any questions? No? What do you find the most interesting? The tape? Yeah, I was just baffled when I was like, you just took tape and you ripped it off. So that's what they were talking about in the podcast, and they won a Nobel Prize for that, which is crazy because you're like, come on. But they were trying really hard to try to figure out a way to make a single layer, and it was really a simple answer. All right, so what I'm going to do then for next time when I see you guys is I'm going to start you on your internal. I'm going to recommend some videos to watch first so that we can kind of understand the big picture and the interesting stuff of graphene. And then you can start diving into understanding its properties, why it has those properties, and what it could be used for. Okay? That's us.